But the Pythagorean theorem is a big idea in geometry and trigonometry as well. We'll take some notes about some shorthand and things like that, and then we'll look at how to solve these problems. But Pythagoras was a Greek fellow that was a mathematician and I think also a philosopher to some degree. And he lived about 2,600 years ago. And he was noticing something about right triangles one day. And the first thing is we need to kind of define a right triangle. Right triangles have exactly one 90-degree angle. They have exactly one 90-degree angle. Can we make a triangle with two 90-degree angles? It wouldn't be a triangle at all, would it? So if I tried to make two right triangles, it doesn't connect, right?
You can connect it.
No, not if these are 90 degrees. Yeah, you can't do it. So by definition, yeah, if you want to show me how the Idahoans do it, that'd be great. How do you make two right triangles in or two right angles in a triangle?
I was saying it's state level, like how it's shaped. Like, because it has like.
Yeah, but that's not a proper triangle. It's kind of triangle-ish, but yeah, it's not a proper triangle. So some shorthand for triangle stuff, so that we're not having to write these words out every time. The shorthand angle, we simply use a symbol like the greater than or less than. This means angle. That way I don't have to write the word every time because I'm lazy. I think I've been very clear about that in my past. Okay. If it's a right angle, we can draw it like this. So a right angle has a 90-degree angle, and the human eye is pretty good at picking up if something's not exactly right. Now, how I draw it is important. That little boxy thing in the corner tells you that it's a right triangle. Or, I'm sorry, not a right triangle, a right angle. But if I draw it like this, and it looks like a right angle, do not assume that it is. We never assume things in geometry. So this is just an angle. This is a right angle. What if I draw the right angle poorly? What if I draw it like this, but I still put that little boxy thing in there? It's still right. I just drew it badly. This is a right angle. Okay? What if I draw it like this, but I put the little boxy thing in there? It's still right. And no matter how close it looks like it's 90 degrees, unless you know, unless you're told or you can prove that it's 90, you don't make the assumption. Okay? That's a mistake that a lot of students make. So 90 degrees, not 90. It's just an angle. And these both are just poorly drawn 90-degree angles. So if the box is in there, it's a 90. Yeah?
Could it ever be flipped? Like,
Oh yeah, it could. It doesn't really matter what the direction is. Yeah, it could be rotated or flipped or whatever. It'd be just fine. Okay, good question. So the next thing is a triangle. Triangle, we simply just draw a little triangle. So you'll see me use angles and triangles and maybe even the 90-degree angles. Just if I'm writing notes or something, I'll just put those in instead of the words. So it's kind of expected that you'd know that. What about a right triangle? Yeah. hopefully one of the angles looks sort of rightish, right? We got a little squarey thing in there, right triangle. And there's actually a whole math on triangles that's really pretty cool. It's called trigonometry. You'll touch on that a little bit next year, I think. All triangles when I say all, I mean all, have a sum of 180 degrees. So what that means is if you add up the measure of all the angles in any triangle, you will always get 180 degrees. Why did I do that? I don't know. All three angle measures It's an important thing to keep in mind. You can answer a lot of questions knowing that. And we still haven't gotten to the Pythagorean theorem. We're just talking a little bit about triangles here. So, everybody with me? You guys got this? Okay. I'm going to move on to the next page. Leave yourself a little bit of room. We're going to draw a triangle, right triangle. Best you can. It doesn't have to be perfect. So Pythagoras was messing around with triangles one day, and what he noticed was something special. That when he had a right triangle, there was always a hypotenuse. Now the hypotenuse is the longest leg of any triangle, but right triangles always have a hypotenuse. I'll probably just use hype for that in the future. It's a little bit kind of cumbersome to write, but it's fun to draw. I mean, it's fun to say, right? Hypotenuse. Hypotenuse. It's kind of a cool word. The thing about a right triangle is the hypotenuse, the longest side, is always across from the 90-degree angle. Always. No exceptions. It's always across from the 90-degree angle. Now, what Pythagoras was doing was he was measuring a triangle one day that he was messing with, and he had a side length of 4 and a shorter side of 3, and the hypotenuse was 5. And he got to playing with the numbers, and what he noticed is that if he sort of built a box out of the leg of the short triangle, a perfect square where it was a 3 by 3, and then he built a perfect square off the leg of the longer, these are legs by the way, if they're not the hypotenuse, they're legs. And then he built a box, a perfect square off of the 5. And then he noticed something. He said, gosh, if I find the area of all of these boxes, 3 squared equals 9. 4 squared equals 16. So a length times width, or a base times height, right? And he noticed that the 5 squared equaled 25. And then he noticed something really cool about that. That the squares, the sum of the squares, 9 plus 16, equaled 25. And he wondered if that was just dumb luck. Right? Because there's a lot of dumb luck in math. Sometimes it happens. 3 squared plus 4 squared equals 5 squared. So he tried again. He tried a different triangle. We'll come back to this here in just a second. He tried a different triangle that he knew was right. This one was a little bit different. Got a 90-degree angle here. So where's the hypotenuse? This guy, right? That's the long leg. And he saw that this was a 12, and this was a 5, and this was a 13, and he tried it again. He built the boxes off, and he noticed that the square of the two shorter legs equaled the square of the longer leg. 5 squared plus 12 squared equaled 13 squared. 25 plus 144 equaled 169. And that was a true statement. And so he came up with his theorem. And he tried many, many other triangles. Every time he tried it, he came up with the same results. That the sum of the two smaller sides squared equaled the square of the long side, the hypotenuse. So he came up with the formula a squared plus b squared equals c squared, where a and b are the two short legs. It doesn't matter which one you call which. It just doesn't matter. Call one a, call one b, it doesn't matter. But the long leg, the hypotenuse, was always c. And the hypotenuse is always across from the what? The right angle. Yep, always across. Now, both of these triangles are called Pythagorean triples. They're called Pythagorean triples because the numbers are even. So there's no decimals or fractions or anything like that in there. It's just they're whole numbers. And in fact, there are lots of Pythagorean triples. These are just a couple of common ones. But he called the 3, 4, 5 his perfect right triangle. Or perfect right triangle, right? This is perfect right triangle. And there's a really cool thing about the 3, 4, 5. Get something here, real quick tool. Can't really show this on video, so I'll shut my video down.